Hi everyone, this video is going to be on average atomic mass, which stands in contrast to our work with mass number when we were looking at the contributions to mass made by the subatomic particles, protons, and neutrons. Here what we're looking at instead of an individual atom is a large sample of atoms. In fact, as large a sample as we can possibly get. What we really want to pin down in this video is the idea that on the periodic table, you see in that top right-hand corner, it gives you what they call an atomic mass. But you'll note all of those masses are very weird-looking decimals. And the reason behind that is this is supposed to be representative of all atoms of nitrogen or carbon or oxygen, whichever element you're looking at. That stands in contrast to just having one atom, where you can see specifically how many protons and neutrons it has and add those together to get to its mass. So we'll take a look at how this atomic mass that's reported on the periodic table is really a weighted average of the masses of all the naturally occurring isotopes of that particular element. So a bigger picture view of mass rather than a zoom in on an individual atom. So over on the left-hand side of your screen, we've got the periodic table box for neon, showing some things that we know and some things that are still unfamiliar to us. In this bottom left in bold, we've got the atomic number, which you know stands for the number of protons. And in this top, I've copied down what the periodic table says about atomic mass. Now we know atomic mass is a reflection of something having to do with protons and neutrons. If you look at an individual atom, mass equals protons plus neutrons, and that's going to give you the mass number. It so turns out that neon has three naturally occurring isotopes: neon 20, neon 21, and neon 22. And in this table, I've reported the more precise masses of those three isotopes. Oftentimes, Regents exams will give you these very precise masses with more significant figures than our traditional isotopic notation might show. So, for example, neon with a mass number of 20, really, when you measure it in AMUs, comes out as 19.99 AMU. Same deal with neon 21 and neon 22. If we're given these precise masses, chances are we're going to use them. What this tells me is I've got three different options for a mass number for neon. So this number up here has to reflect the fact that there isn't just one type of neon around and available. In fact, if you dig a little deeper into chemistry knowledge, what you're going to find is that each three of these isotopes has a different frequency in which they show up in nature. Some are more common than others. And in fact, neon 20 is the most common, coming out at 90.9% relative abundance or percent natural abundance. What that just tells me is that about 91% of all neon atoms have a mass number of 20. On the other hand, only about 0.3% have a mass of 21, and about 8.8% have a mass of 22. We're going to take this into account when we try and calculate the average atomic mass of neon. So what that says is, on average, if I reach into, let's say, a bag of neon atoms, what am I most likely to pull out? And what exactly is the weighted average of all those different options? So in order to get a weighted average, we do something like your gradebook does for you when it's trying to calculate a grade for you in the class. In gradebook, we take the percent that thing is worth. So in my class, tests being worth 65% of your grade. And then I multiply it by your test score. So in this case, what I've got is a percent natural abundance, 9%, and a score, or in this case, a mass, of 19.99. Now, what's important is, just like percents in the gradebook are percents out of 100, in this case, we want to make sure that these percents are reflective of being out of 100. So I'm going to write in the divided by 100 component in order to help me sort of figure this business out. Neon 20 isn't the only thing contributing to my average atomic mass. I've got a little teeny tiny contribution from neon 21 as well. So I'm going to say 0.3% out of 100 is contributed that has a mass of 20.99. And finally, the remaining 8.8% has a mass of 21.99. So what we see in this calculation is that average atomic mass is always equal to percent abundance times mass plus percent abundance times mass as many times as we need to include all naturally occurring isotopes of that element. Sometimes that'll be 2, sometimes it'll be 3, could be 5, you never know. So whatever they give you, that's going to be how many terms will be in your equation. And this percent, remember, is going to be out of 100. So I usually do this divided by 100 business so that I don't have to convert to decimals right away. But if you are asked to solve, that's exactly what you're going to end up doing, is just take a piece of that equation at a time. So 90.9 divided by 100 is 0.909 times 19.99 plus, and this is why I don't typically convert to decimals to begin with, is people tend to mess this type of conversion up. 0.3% is equal to 0.003. I'm going to multiply that by 20.99. And this 8.8 is 0.088 times 21.99. At this point, you can let your calculator do the work for you. When I plug all this into my calculator, what I notice is that I dropped a plus sign right in between these two isotopes. But at the end of the day, what I end up getting is an average atomic mass of 20.17. And that's going to be in units of AMU. Now you notice that doesn't precisely match what's given to you on the periodic table. That's probably because we've had some variation in our natural abundance, or maybe our measurements of mass in AMU aren't quite as precise as the measurements that were used to get this number. What I do notice, though, is that 20.17 is a heck of a lot closer to 20 than it is to either of the other two naturally occurring isotopes of neon. And what that tells us is that neon-20 is the most common or the most abundant isotope or form of neon. So whenever you see this number on the periodic table, it does not tell you the mass of an individual neon atom. What it does give you a clue to, though, is what the most common mass of a neon atom is. And that's just going to be whatever this number is, rounded to the nearest whole number. So what that tells me is, because this number is very close to 20, that must mean 20 is the most popular choice for mass number when we look at the isotopes of neon. So from this, make sure you're feeling comfortable identifying the most common isotope of a particular element given its average atomic mass. Make sure you're very comfortable using this equation to calculate average atomic mass, because what you're going to notice is that this is not on table T on your reference tables. You're going to have to be able to produce and use this equation independently. So make sure you know what each individual component stands for, and that you feel confident solving algebraically when you've got the numbers to plug into each piece of the equation.